Hi folks, let's continue with our discussion of finite state machines. So far we've been considering fairly simple finite state machines, and we've only allowed them to have digital inputs and digital outputs. Remember, the digital inputs are all of those inputs that are on the transitions, remember the arrows between the states. And I know in the previous diagrams I didn't typically list the input names, the S and the R that are on this one, but I pulled on the old diagram. But we only allow them to be digital values, 0 and 1. We'd typically have a string there of as many digits as we had digital inputs. And the digital outputs, remember the outputs are the below the line in the state. We've only allowed those to be digital. So there's no PWM outputs. There's no analog inputs. Everything's been strictly digital. We also did not allow any sort of memory. We didn't allow any sort of tracking of any memory beyond those couple of memory bits that we use to record what state we're in. So that has been our restriction up until now, but we are going to lift that restriction, and I'm going to show you how to incorporate memory. For the moment, we're still going to stick with the mostly digital inputs and outputs. So let's consider, as an example, a garage door. And so, like many garage doors out there, the one on my garage in the backyard has a remote button. Now mine's in my car, but when you press the button, the garage door goes up, and you press it again, and the garage door comes down. Fortunately, there's also a limit switch on each side of the garage door, so when I press the button, it goes all the way up until it hits the limit switch. And when I press it again, it's going to come all the way down until it hits the limit switch. That way it doesn't go too far, right? So we have some hard stops. We have those limit switches to control the action. And we'd like to model this as a finite state machine. So pause the video, model it as a finite state machine, and then we'll continue. All right, so I'm assuming that by now you have modeled it as a finite state machine and you're ready for me to show you my solution. So here's what I have with 2 inputs and 2 outputs and 4 states. So the inputs are going to be the button on the remote and the limit switch. And I'm going to assume that both limit switches at the top and the bottom are merged together into a single input. You know, that either one of them triggers, it's going to trigger this limit switch input, so we're ORing them together. The outputs are going to be power to the motor, so are we turning on the motor, are we turning off the motor? And also the direction that the motor is going. Is it going up or down? In this case, going up is going to be considered a 0, and going down is going to be considered a 1. So if we start in state S0, we assume that the door is closed, and so nothing's happening. The motor's turned off. The direction doesn't really matter, but I'm leaving it as a 0. Just you'll have to have something there. I am going to, because I didn't do this in my original diagram here, I'm also going to add in a transition from S0 to S0, because if I get a 0 on the button and an X on the limit switch, because I don't care about the limit switch at that point, then it's going to stay closed. But as soon as I press the button, that's the 1X on the next transition here, then the door starts to open. And the door will continue to open until the limit switch is hit. So that's going to be an X0. So regardless of the button press, the door will continue to open until the limit switch is hit. And then when the limit switch is hit, that's the X1, then the door is going to be fully open and it stops moving. So we turn off the motor power. That's the 0, 0 again. And we're going to hang out there as long as nothing interesting happens, which is to say we don't get any sort of button press on the remote. And then if the button is pressed on the remote, we'll start closing again, and we'll continue closing until we get nothing on the 1X on the remote button. We don't care about that. And we'll continue to close as long as we don't see the limit switch. But as soon as we see the limit switch, so that's an X1, we'll know that the door is all the way closed. So 4 states, 2 inputs, 2 outputs, very simple finite state machine, and we can represent a very simple garage door. But this might not be the best garage door. So what if we want to add an additional layer of complexity? So the garage door is going up and it's partway up, and we hit the button again. What happens? Well, on most garage doors, it stops. And then if you press it a third time, it goes the opposite direction. So, my son opens the drawer and hits the button and the door goes up and I say, what in the world are you doing? So we stop it and we send it back down. So we'd like to be able to do that in both directions. If it's coming down and you press the button, you can stop it and send it back up. So we're just going to reverse the direction. So let's go ahead and do that as a finite state machine. Again, pause the video, draw your own finite state machine, and then we'll continue. All right, let's look at my solution. So it's more complicated. Let's start in S0. I forgot to add my initial state indicator on the previous one. I'm sorry. But there's my initial state. We'll start in S0. And just like before, when I made these slides, I forgot to include that transition from S0 to S0. So as long as there is nothing happening on the remote, so that's a 0x, it's going to stay in S0 with the door closed. And then once we see the remote pressed, that's the 1x, we transition to S1, and so the door is starting to open. And what is going to be the condition that we continue to sit there? Well, as long as we don't see any remote button and we don't see a limit switch, we're going to continue to open. If we do see a limit switch and we don't see a remote button, then we know that the door has gotten all the way open and we're going to move to S2. But if we see the remote being pressed, that's the 1, 0 here, we will transition to S4 and we will be stopping. So we're stopping while we're opening. Oops, there's an error there. That should have been a 0, 0, and that should have been a 0, 0. Sorry. So we're going to stop while we're opening. And notice the stop while opening and stop while closing are two different states. And the reason for that is the next states are different, so they're not equivalent. So if we were going up and we see that remote pressed, we go to S4, we stop while opening, and we sit there and we wait there. So put that loop in there. We wait there until the remote gets pressed again. So, yeah, I know that this pen keeps causing it to jump across. I've never figured that one out. It seems to be a Windows problem. So we're going to wait there until the button's pressed again, so that's a 0x. And when the button is pressed again, that's the 1x here, we transition to the door closing because we've reversed direction, and now the door is going to close. And so as the door is closing, same sort of thing. If it gets all the way to the limit switch, we're at the S0 and the door is fully closed. If the door is closing and we see that remote button again, well, then we stop while closing. Same sort of problem. We need to put in that loop back from S5 to S5 with the 0x condition on that. And if we're stopped while closing and you see the remote button, then we go back to the door opening. And let's just go ahead and for completeness, put in these here, that if we're in the door closing and we don't see the remote and we don't see the limit switch, we continue closing. And if we're in the all the way open case, we're going to hang out until the button is pressed. So that's a 0x. Now, if you remember talking about making sure that we get all the different input combinations, you'll notice I'm actually missing a few. If we're in S1, so if we're in S1 and you get a 0, 0, we stay in S1. If you get a 1, 0, we go to S4. If we get a 0, 1, we go to S2. I haven't included the 1, 1 case. And that one, I'm going to leave that as a design decision for you. What happens if the remote button is pressed and the limit switch is triggered at exactly the same time? Chances of that are extraordinarily low, but it's possible. So we ought to know what's going to happen, and it should be encoded somewhere here. If the limit switch is hit, I'm assuming that the door is fully open, and so we're good. So I would probably put it here. So the 0, 1 or the 1, 1 case is going to result in the door being fully open. I think that's a reasonable way to put it. And so we would do the same over here. If the 1, 1 case or the 0, 1 case hit, then the door would be fully closed. So there we go. We got to find a state machine that's a bit more complicated, but it does allow us to handle what happens if the button is pressed while the door is going up or down. But let's add even more complexity. Lots of garage door openers have a light on them, and that light is there to help you out, you're fumbling around in the dark. Anytime you press the button, it's going to bring the light on and say, well, there's somebody here that might want to see what they're doing. And so let's assume that that light is going to stay on for 4.5 minutes. Why 4.5 minutes? I don't know. 4.5 minutes after the button is pressed. And so how are we going to do that? Well, we're going to assume that there is some sort of external timer that's going to keep track of the time for us. So there's some device that this garage door opener logic is going to communicate to that will count the time. So we're going to create a new output that triggers the timer. We're going to create a new input from the timer to understand when the timer has finished counting 4.5 minutes. That's the timer expired. And so now we're going to have to consider that light every time the button is pressed. Wow, that's a lot of additional stuff. And so if we had this diagram and we have to consider the light being on or off every single time, our states are going to double. And so instead of having 4 states in our original case, or 6 states in our slightly more complicated case that we can interrupt the up-down motion, now we're going to have 12 states. And so you can see that as we're adding the complexity, we are very quickly blowing up the number of states. And so hopefully you're looking at this and saying, there should be a better way to do this. And of course there is, and we're going to do that next. So let's make some structural changes to the problem. Let's consider that the door and the light, while they are interrelated, are actually operating as 2 separate finite state machines. And they could still be operating on the same piece of hardware, but it's going to implement them as 2 separate finite state machines. Okay, so that's going to help us. And let's also consider adding memory. We're going to add just a little bit of memory. We're going to have the door direction being stored in memory, so that's just a binary number. That's easy enough. And we're going to store the light timer, so that's going to be a little bit more complicated. We're just storing a number of seconds or minutes or however you want to store it. Probably seconds is the easiest, but depending on your hardware, maybe microseconds or milliseconds makes more sense. But we're going to store the timer. So we got 2 things that we're storing in memory, and we're going to split this into 2 finite state machines. So let's look at it. We'll consider the door first, and then we'll consider the light. So on the door side, we're going to have the same inputs, the button and the limit switch. We're going to have the same outputs, the motor power and the direction. And all I'm doing is I'm adding memory. And so I'm going to add 1 memory element here for the door direction. I'm going to call it lowercase d. I will say that much like some of the other things I showed you, this is not any sort of like standard terminology. This is what works for me. I'm not sure that there is a great standard terminology for this one, but here's what we're using in this class. So I've got 2 states. I've got the door stop state and the door moving state. Now, because I'm storing the direction, I no longer need to have a door going up state and a door going down state, because the directionality is something I can get from the memory, so the door is just moving or not moving. And so let's start with, again, let's put in our initial state indicator. Sorry, I missed that on the first one. So there's my initial state. We're going to start in S0. The door is stopped. And so ignore the toggle direction. I'll come back to that. So in this case, in this state, the outputs are going to be 0, 0, so nothing's turned on. And we're going to stay here until the button is pressed. So that's the 0x over here. When the button is pressed, that's the 1x, we transition from S0 to S1, and now the door is moving. And so what I'm going to say here is I'm going to hold the direction. There's no change in the direction. It just is the direction. And I am going to let my output be that the motor is turned on and the direction is determined by the memory element that we're calling D. And so we will continue with that as long as we do not hit a limit switch and we do not see a button. If we see the button press without a limit switch, or we see a limit switch without a button press, or we see both of them, then we stop. And when we stop, we're going to toggle the direction. What does it mean to toggle? Well, if we were going up, then when we stop, we're automatically going to switch the direction to down. So when we start moving, we'll be moving down. And if we stop again, we'll toggle it back to up. And so every time that we go from the door moving to the door stopping, we're going to toggle the direction. Okay, this is not hard. This is a relatively simple thing to implement, and it's a lot simpler than what we were looking at when we added the light to the previous one. It's even simpler, honestly, than the 6-state version that we already did. But now we can add in the light and get, again, a relatively simple way to do this. So for the light, we're going to consider the button being pressed. We're going to consider, again, the timer expired as an input. And it's sort of a fictitious input because we're going to take it from the memory element, but I'm going to treat it as an input for the transitions. And we're going to have the output is going to be the light, just on or off. And we're going to have one memory element. And the memory element is going to be the remaining time. Now, again, how you track it kind of depends on your hardware. It could be in milliseconds, could be in microseconds, could be in seconds, could be in minutes. Really depends on your hardware, but it's some length of time, and we can store that in a variable. So let's start in state 0. So put in our initial state here. In state 0, the light is off, so we're going to set T to 0 because we don't need it right now. And the output is 0. And we're going to stay there as long as we don't see the button pressed. So that's the 0x in the transition. When we see the button pressed, the 1x here, we're going to transition to state S1. And in state S1, we're going to turn on the light. That's the 1 in the output. And we're going to set a value for our memory. We're going to set that to 4.5 minutes. And then we're going to always, that's the XX here, transition immediately to S2. And when we transition to S2, notice that it's got the same output, but it's going to have different memory behavior. So in this case, S1 sets a value for the memory, and S2 is going to allow the memory to count down. And it's going to count down until such time as we see the button pressed again or the timer is expired. So if the button is pressed again, regardless of what else is going on, we reset the timer. So that's the going back to S1 where it's going to reset it to 4.5 and then immediately come back to S2 and start counting down again. And if we see the timer is expired, but there hasn't been another button press, we'll go to S0 and wait with the light turned off. And so why did I separate S1 and S2 into two different states? I did that because I wanted to have two different memory operations. And I thought, for my own purposes, that makes sense to separate that out, that one of them is setting a value for the memory and the other is letting it count down. If I considered them to be together in one state where I was going to set it and then let it count down, then what happens when I'm in that state and I get the button press? Because when the button press comes in, I should then reset the memory and start letting it count down again. But if there's not a state transition, then it starts to sound a bit more like a Mealy machine instead of a Moore machine, where the input and the state are combined in order to determine the output, or the memory effect in this case. I didn't like that personally. I like it like this. It's much more of a Moore machine, where the state is controlling how the memory is being dealt with. So, again, there's not, as far as I'm aware, some sort of great system for this. This is how I do it. I've kept that same structure that we had before in terms of, having a name and having outputs, and then in the middle I've just added the memory. So if you talk to computer science people, my understanding is that this would be classified as, these two at least, would be classified as push-down automatons. And so the push-down ones are going to have a finite state machine with a single memory element that's at the top of the stack. What's a stack? Don't worry about it. It's a memory element. So our two finite state machines in this example, where each one of them has access to one memory element and it's just dealing with the one memory element, fine. That's a push-down automaton. If you go beyond that and you want to have multiple memory elements and whatever, you're getting into a Turing machine. And that is in the realm of computer science. That is not my area and probably not yours either. So unless you're going to go take courses over there, which is great, go do it. I am going to just put all of that aside and say that what we're discussing here is just finite state machines with memory. And we're just going to leave it at that as finite state machines with memory. Our finite state machines with memory are going to look like this. We still have outputs that are digital. We still have, well, We still have outputs that are digital, but they might be tied to the memory. We still have state transitions that are based on inputs that are digital, but we do have memory that is available and can be used in these things. Yeah. So let's set that aside, and we'll move on then to the next topic.